Right now, Earth is moving at 1.4 million miles per hour towards something massive, invisible, and hidden directly behind our own galaxy. You have never felt it. You will never feel it. And for most of human history, we had no idea it was happening at all. 100,000 galaxies, all being pulled in the same direction, toward a gravitational source so enormous it sits behind a wall of dust we cannot see through. And the strangest part, we will never actually reach it. The Great Attractor, the Shapley supercluster, the void pushing us from behind. If you enjoy deep investigations like this, subscribe now. The investigation starts with the oldest light in the universe. Right now, you are moving. You feel nothing. Your coffee sits still in its cup. The room around you seems perfectly quiet, and yet you are hurtling through space at a velocity that would reduce a spacecraft to vapor, and most people have never heard the full number spoken out loud. Start with the layer everyone knows. Earth orbits the star at the center of our solar system. That orbit spans roughly 600 million miles per year. Work out the math, and Earth moves at around 67,000 miles per hour relative to that star. 67,000 miles every hour, without pause, without variation. You never feel it because the atmosphere, the oceans, and the ground beneath your feet are all moving with you. When you sit inside a moving car, you feel no wind from inside. Same principle, vastly bigger scale. But that is only the first layer. Our entire solar system is also orbiting the center of the Milky Way. That orbit is almost incomprehensibly large. One full lap takes around 225 million years. The last time our solar system stood at this same point in its orbit around the galaxy, the ancestors of dinosaurs were only beginning to appear on Earth. To hold that orbit, the whole solar system must move at roughly 500,000 miles per hour, 500,000 miles per hour. Still no sensation of movement. Now comes the third layer. This is where it gets strange. The Milky Way itself is moving. Our galaxy, together with Andromeda, the Triangulum galaxy, and about 50 smaller satellite galaxies, forms a gravitational cluster called the local group. The local group is not standing still. Scientists measure its motion by comparing our position against the cosmic microwave background, the oldest light in the universe, a faint glow left over from the Big Bang. That comparison yields a speed. The local group moves at approximately 1,400,000 miles per hour relative to that ancient light. In the units physicists use, that is 630 kilometers per second, 630 kilometers per second. In the time it took you to hear that sentence, everything you have ever known moved roughly 60 miles through space. Now here is what separates this from a simple fact about the expanding universe. That motion has a specific direction. The local group is not expanding outward randomly. It is streaming, aimed at a particular region of the southern sky. Something out there is responsible. A gravitational source is pulling us toward it, or some force is pushing us from behind. Astronomers are still working out the exact mechanism, but the flow itself is confirmed science. So what is it? What kind of structure could exert gravitational influence over an entire group of galaxies spread across millions of light years? How massive would it need to be? And if it has been pulling us for billions of years, why did we spend most of human history with no knowledge of it at all? The answer took decades to build. It required instruments that did not exist until the latter half of the 20th century. It required 7 astronomers willing to stake their careers on a claim their colleagues called impossible. It begins with the oldest light in the universe. Encoded in that ancient glow was the first precise clue about where we are being taken. The Big Bang left behind an afterglow. This is confirmed science, not speculation. About 380,000 years after the universe began, the temperature dropped just enough for electrons and protons to combine into neutral atoms. For the first time, light was free to travel. It poured out in every direction simultaneously. That light has been traveling ever since, stretched by the expansion of the universe into microwave wavelengths, filling the entire sky from every direction at once. We call it the cosmic microwave background. Physicists detected it by accident in 1965. Two engineers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were testing an antenna originally built for satellite communications. Every direction they pointed it, they picked up a faint, persistent noise they could not explain. They cleaned the antenna. They checked every component. They even cleared out pigeons nesting inside the receiver housing. The hiss remained. Eventually, they connected with cosmologists who told them what they were hearing. The remnant heat of creation, arriving equally from every point in the sky. Penzias and Wilson won the Nobel Prize in 1978, equally from every direction. That was the initial picture. A smooth, uniform glow. The same faint warmth everywhere, about 2.7 degrees above absolute zero. The universe, at its largest scale, appeared perfectly smooth. It was not perfectly smooth. More sensitive measurements through the 1970s revealed something subtle. The temperature of the cosmic microwave background was not identical in every direction. One half of the sky ran microscopically warmer. The opposite half ran microscopically cooler. The temperature difference was tiny, about 1 part in 1,000. Physicists call this the temperature dipole. The most precise early measurement was confirmed around 1977. That dipole is a fingerprint. It reveals motion. Here is the physics. When you move through a medium that fills all of space, the waves in front of you get compressed, and the waves behind you get stretched. Move toward a sound source, and the pitch rises. Move away, and it drops. The same physics applies to the cosmic microwave background. If everything we know is moving through space, the background should appear slightly hotter in the direction of motion and slightly cooler in the opposite direction. That is exactly what the measurements showed. The dipole told physicists, "You are moving." It named the direction. It gave the speed, roughly 630 kilometers per second relative to the background rest frame. The entire local group, flowing at 1,400,000 miles per hour, aimed at a particular patch of sky. What the dipole did not say was why. It measured the motion with precision. It offered no explanation for the cause. It was like finding enormous tracks pressed into sand and being able to measure the stride length, the depth, the exact bearing, and having no idea what made them. Something was generating this flow. The dipole confirmed it was happening, confirmed the scale, confirmed the direction, and then it went silent on every question that actually mattered. The tracks were real. Tracing them back to their source would take another decade of work, a new measurement technique, and 7 researchers who were about to spend years mapping the motions of galaxies one by one. In 1980, 7 astronomers began a project that would, within 6 years, force cosmologists to rethink one of their most fundamental assumptions about the universe. Their names: Sandra Faber, Alan Dressler, Donald Lyndon Bell, David Burstein, Roger Davies, Roberto Terlovich, Gary Wegner. They became known later as the 7 Samurai. The nickname came from colleagues who found their ambition both admirable and alarming. The project was clean in concept and grueling in execution. They wanted to measure how galaxies were actually moving through space. Their real, physical, peculiar velocities, not the apparent motion caused by cosmic expansion. To do that, they needed precise, independent distance measurements for hundreds of galaxies spread across the local universe. They developed and validated a technique called the dn sigma method. Elliptical galaxies, the large, smooth, roughly football-shaped galaxies scattered through the cosmos, have a measurable internal property: the spread of stellar velocities inside them. That velocity dispersion correlates tightly with the galaxy's true brightness and physical size. Measure the dispersion, calculate the true brightness, compare it to how bright the galaxy appears from Earth, and you extract its distance, without depending on any assumptions about the expansion of the universe. An independent ruler, built from the internal physics of the galaxies themselves. Over years of telescope observations, the team measured hundreds of elliptical galaxies across a wide region of the local universe. What they found stopped them. Every galaxy had a peculiar velocity. That was expected, but the peculiar velocities were not random. They were not pointing in scattered, independent directions. The galaxies were flowing, coordinated, converging. Hundreds of them, spread across a region hundreds of millions of light years wide, all streaming toward the same point in the southern sky. Their speeds ranged from 600 to 700 kilometers per second. The team published in 1986 their conclusion: something enormous sat in the direction of that flow. A massive concentration of matter generating the gravitational pull behind those velocities. They called it the Great Attractor. The scientific community did not celebrate. The problem was that this violated something cosmologists had taken as a baseline assumption. The universe, at large enough scales, was supposed to be smooth, matter distributed roughly evenly. No single structure enormous enough to dominate whole regions of the sky. The standard models predicted that peculiar velocities would be modest, local, and independent. What the Seven Samurai were claiming was that a vast region of the universe was gravitationally organized around a single dominant source. Colleagues raised objections. The Dean Sigma method was relatively new. Maybe the calibration had systematic errors. Maybe the sample was biased. Maybe the flow was real but smaller than reported. Some of those objections were fair, but the Seven Samurai had done their work carefully. The data held. Hundreds of galaxies pointed the same direction, and that direction aimed straight into a region of sky where direct observation was almost impossible. The discovery survived every challenge to its core. What did not survive was the team's estimate of exactly how massive the attractor was. That number was wrong, badly wrong, but no one knew it yet. The bigger problem right now was that they could not see it at all. There is a region of the sky that optical astronomers essentially cannot use. It runs as a wide band across the entire celestial sphere, following the plane of our own galaxy. At its thickest, it spans tens of degrees. Astronomers call it the zone of avoidance. Behind it sits roughly 20% of the observable universe, hidden from the most powerful ground-based and space-based optical telescopes alike. The reason is dust. The Milky Way is a flat disk of stars, gas, and dust hundreds of thousands of light years across. We live near the outer edge of that disk. When we look toward the galactic plane, we look through the thickest part of it. The dust in that plane absorbs and scatters visible light with extraordinary efficiency. Galaxies that would be bright and observable from other directions simply disappear behind it. An entire strip of the cosmos goes dark. The Great Attractor sits almost exactly inside that strip, the point in the southern sky where hundreds of galaxies were converging. The gravitational target the Seven Samurai had identified from years of painstaking measurements fell almost precisely behind the densest portion of our own galaxy's dust plane. The answer to one of cosmology's central questions was hidden behind the one obstacle we could not remove. Picture what this meant for a researcher in the late 1980s. You have the velocity data. You have confirmed the flow in hundreds of independent galaxies. You know approximately where to look. You apply for telescope time, wait months for your observation window, and then point the world's finest optical instruments at that region of sky. You see nothing useful. The dust swallows everything. The Great Attractor, if it exists as described, is sitting behind a wall that optical instruments cannot penetrate. You can infer it from the motions of surrounding galaxies, the way you might infer a whirlpool from boats moving on its edges. Direct observation was gone. Astronomers tried working around the edges. The zone of avoidance is thinner in some parts of the sky than others. Surveys crept as close to the galactic plane as they could, sampling regions just above and below it, trying to extrapolate inward. It helped. It was not enough. Without direct observation, mass estimates relied entirely on the surrounding flow patterns. Different assumptions plugged into those estimates produced wildly different answers. The uncertainty in the Great Attractor's mass spanned orders of magnitude. Some estimates were reasonable, some were enormous. Without seeing the object, there was no way to anchor the calculation. The zone of avoidance was not just a technical inconvenience, it was structural. We happened to live inside the disk of a galaxy whose own dust plane sat almost precisely in front of the most important gravitational structure in our cosmic neighborhood. Our position in the galaxy was working directly against us. This had real scientific consequences. The debate over whether the Great Attractor was real, whether the mass estimates were credible, whether the Seven Samurai had made a genuine discovery or a systematic error, could not be settled while the thing itself remained invisible. Seeing through the dust required leaving visible wavelengths behind entirely. X-rays passed through galactic dust. The instruments to use them were being built. When they turned toward the zone of avoidance, what they found immediately changed the picture, and what it revealed was both more satisfying and more troubling than anyone had hoped. The dust that blocks visible light is nearly transparent to X-rays. This is basic physics. X-ray photons carry much higher energies than visible photons, and the dust grains that absorb visible wavelengths have almost no effect on X-rays passing through. If a massive cluster of galaxies sat behind the zone of avoidance, the superheated gas trapped within that cluster would radiate X-rays, and those X-rays would travel through the galactic dust essentially unimpeded. ROSAT, the Röntgen satellite, launched by Germany in 1990, gave astronomers their first true all-sky X-ray survey. It orbited Earth for 9 years and built up an image of the entire sky in X-ray wavelengths. When researchers turned that image toward the galactic plane, they found galaxy clusters that optical surveys had never detected. A follow-up project, the Clusters in the Zone of Avoidance Survey, known as CZUR, extended this work systematically. By the early 2000s, it had found more than 200 galaxy clusters hidden behind the galactic dust, invisible in visible light, glowing in X-rays. Near the center of the Great Attractor region, one cluster stood out from all the others. The Norma cluster, catalogued as ACO 3627, sits about 220 million light-years away, directly behind the galactic plane. X-ray observations revealed it to be massive, containing thousands of galaxies, with the temperature of its intracluster gas indicating enormous gravitational depth. Its mass came in at roughly 10 to the power of 15 times the mass of our star. In cosmological terms, that is a genuinely large galaxy cluster. For a moment, it seemed like the answer. The Great Attractor had been described as a single dominant object hiding behind the zone of avoidance. Norma was a dominant object hiding behind the zone of avoidance. Many researchers assumed Norma was the Great Attractor, or at least its core. Then they ran the numbers. Norma's mass, while substantial, was not nearly large enough to account for the observed velocities. The gravitational pull from a cluster of 10 to the power of 15 solar masses at that distance generates a specific and calculable flow. That flow was smaller than what multiple surveys had measured. Norma could explain part of our motion. It could not explain all of it. The original picture needed revision. The Great Attractor was not a single giant object. It was a gravitational basin, a broad region where matter had concentrated more heavily than average, and Norma was the largest known node within that basin. But the basin was more diffuse, more spread out, and less dominated by any single object than the original description implied. This was a real intellectual setback for the single object model. The thing people had been imagining as one monstrous galaxy cluster resolved, under X-ray light, into a collection of moderately large structures in a gravitationally overdense region, and it raised a harder question. If Norma and the broader Great Attractor basin together could not fully explain our observed velocity, something else had to be contributing, something farther away, something that had been considered too distant to matter. that something had a name. It had been catalogued for decades. And, until recently, almost no one thought it was relevant to local motion. In 1930, a British-American astronomer named Harold Shapley catalogued an unusual concentration of galaxies in the constellation Centaurus. It was distant enough that for decades, most cosmologists simply filed it as a curiosity, a large cluster, far outside our cosmic neighborhood, probably not relevant to local dynamics. They were wrong. By a large margin, the Shapley supercluster sits approximately 650 million light-years from Earth. That is roughly 4 times farther away than the Great Attractor region. Distance in cosmology usually means diminishing relevance. Gravitational influence falls off with the square of the distance. Something 4 times farther away exerts 16 times less gravitational pull at a given mass. For Shapley to matter to local dynamics, it would need to be extraordinarily massive. It is extraordinarily massive. The Shapley supercluster contains more than 8,000 individual galaxies. Its total mass runs to approximately 5 times 10 to the power of 16 solar masses. Written out fully, that is 50 quadrillion times the mass of our star. It stands as one of the largest gravitationally concentrated structures within several billion light-years of Earth. For most of the late 20th century, the assumption was simple. Shapley was too far away to contribute meaningfully to the motion of the local group. The Great Attractor region was the dominant gravitational influence. Shapley was background noise. Mid-2000s surveys began dismantling that assumption. Researchers tracing the precise motion vector of the local group found that the flow did not stop at the Great Attractor. If the Great Attractor were the sole explanation, the velocity vector would point directly toward its center, and the surrounding galaxy flow would converge there in a way that matched. Instead, the velocity field continued past the Great Attractor, pointing farther in the direction of Shapley. Multiple independent analyses confirmed this. The motion of the local group, when compared carefully to the gravitational landscapes of both structures, showed contributions from both. Shapley, despite its distance, was adding to our velocity nearly as much as the closer attractor. Its enormous mass compensated for its enormous distance. Think about what this means. For most of the 20th century, cosmologists had been trying to explain a velocity with one gravitational source. When Norma turned out to be smaller than expected, the budget still needed filling. Shapley, 650 million light-years away, was filling a significant portion of it. The picture was becoming larger. Literally, the gravitational influences shaping our path through the universe were not local. They extended across distances that had previously been considered irrelevant to local dynamics. There is something disorienting about this. It means the forces determining where Earth and everything on it is heading reach far beyond what anyone initially assumed. Gravitational geography operates at scales our intuitions are not built to handle, but the velocity budget was still not complete. Great Attractor plus Shapley brought the numbers closer. They did not close the gap entirely, and meanwhile, the original mass estimates for the Great Attractor were about to be revised in a way that humiliated those who made them and vindicated those who doubted them. Scientists are supposed to be wrong sometimes. It is how the process works. You propose, you measure, others measure. The data eventually wins. The Seven Samurai knew this. They had spent years building their case with the best distance measurement techniques available in the 1980s. Their core finding held. The flow was real, the Great Attractor was real. Their mass estimate was not. The original figures attached to the Great Attractor were enormous. Various estimates placed its mass at several times 10 to the power of 16 solar masses or higher. This was mathematically necessary to explain the observed flow velocities at the inferred distances. If the object is that far away and pulling this hard, it must be extraordinarily heavy. The logic was internally consistent. By the early 2000s, X-ray surveys had mapped the actual galaxy cluster content of the Great Attractor region in real detail. The Norma cluster was the dominant structure. The surrounding region contained additional clusters, but none of them were exceptional. When researchers totaled the actual observed mass of all structures in the Great Attractor basin, the sum fell far short of the original estimates. The revision was not modest. The corrected mass figures came in at roughly 90% less than what had originally been claimed, a factor of 10 off. The critics who had argued the Seven Samurai were overstating the scale turned out to be largely correct. The scientific community absorbed this in predictable ways. Researchers who had doubted the Great Attractor from the beginning cited the revision as vindication. Papers that had leaned on the earlier estimates quietly updated their references. The Seven Samurai faced the particular professional discomfort of being right about the important thing and badly wrong about the details that gave the important thing its drama. But here is what actually matters. The core discovery survived completely. The flow was real. Hundreds of galaxies streaming toward the southern sky at hundreds of kilometers per second that remained firm in the data. The Great Attractor region existed as a genuine gravitational overdensity. Norma was real. The basin was real. What died was the idea that it was big enough, alone, to explain everything. The downward revision of the mass forced the field to look farther. It forced Shapley to take center stage. It forced acceptance that the local group's velocity was not the product of one enormous nearby structure, but a sum of contributions from multiple large-scale gravitational sources spread across hundreds of millions of light-years. The story had shifted from a single answer to a web of answers. One dominant object had become a gravitational system, and the tools to map that system fully did not yet exist. Building those tools would take two scientists working on opposite sides of the planet, compiling one of the most ambitious observational datasets in the history of cosmology. What they built would not just clarify our motion, it would give the Milky Way something it had never officially had, an address in the universe. Mapping how galaxies actually move through space requires solving a layered measurement problem. When you observe a distant galaxy, you can measure how fast it is receding from us. But that recession is two things at once: the expansion of the universe pushing everything apart, and the galaxy's own peculiar velocity, its individual motion driven by local gravity. To isolate the peculiar velocity, you need an independent distance measurement. Know the recession speed and the true distance. Subtract the expected Hubble expansion, and what remains is the peculiar velocity, the galaxy's real, physical motion through the gravitational landscape. This sounds clean. Across thousands of galaxies spread over hundreds of millions of light-years, it is an enormous undertaking. Brent Tully at the University of Hawaii and Helene Courtois at the University of Lyon began building exactly this kind of dataset in the early 2000s. Their project became known as Cosmic Flows. The goal was the largest, most precise catalogue of galaxy distances and peculiar velocities ever assembled. The purpose was to use that catalogue to reconstruct the gravitational velocity field of the local universe. The first generation, Cosmic Flows 1, established the methodology and proved it could function at scale. The second generation, Cosmic Flows 2, gathered data on more than 8,000 galaxies and represented a qualitative leap in coverage and precision. Later generations would push further still. Cosmic Flows 3 and Cosmic Flows 4 eventually incorporated tens of thousands of galaxies across a much wider volume of space. The velocity field they were reconstructing is essentially a map of how gravity is organized in our cosmic neighborhood. Where matter clumps together, the velocity field converges toward it. Where matter is sparse, galaxies flow outward into relative voids. The velocity field is a direct readout of the gravitational landscape, like contour lines on a topographic map of invisible terrain. What Tully and Courtois were building was a gravitational atlas of the universe around us. As that atlas took shape, it revealed something unexpected. The flowing patterns in the velocity field were not simply converging on a few isolated attractors. They were organized on a scale far larger than anticipated. The flows traced coherent structures, regions where the motions of thousands of galaxies were correlated, basins where everything drained toward a common gravitational center. The gravitational geography of the universe was hierarchical in a way that had not been fully grasped before. Individual galaxy clusters sat inside larger superclusters. Superclusters sat inside enormous gravitational basins. The local universe was structured not as a collection of scattered clumps, but as a nested architecture of flows and attractors operating at multiple scales simultaneously. Tully and Courtois were not just measuring velocities, they were tracing the skeleton of the universe around us. One feature of that skeleton, visible in the cosmic flows, 2 data, was so large and so coherent that it demanded its own name. Their result, published in 2014, would give the Milky Way something it had never officially had. And what that something turned out to be would change the way cosmologists thought about where we live. September 4th, 2014, the journal Nature published a paper with a list of authors, led by R. Brent Tully. The paper contained a single central result, built from more than 8,000 galaxy peculiar velocities in the cosmic flows. To catalog, the result was this: the Milky Way belongs to a single, coherent, gravitational superstructure, 520 million light-years across, containing more than 100,000 galaxies, carrying a total mass of approximately 10 to the power of 17 solar masses. They named it Laniakea, from the Hawaiian words meaning immeasurable heaven. Here is what the paper actually demonstrated. The cosmic flows, 2 velocity data, allowed the team to identify gravitational basins in the local universe. A gravitational basin is defined by flow. If the peculiar velocities of all galaxies in a given region ultimately converge toward the same gravitational center, those galaxies belong to the same basin. They are bound by their shared trajectory, even if they are currently hundreds of millions of light-years apart from each other. The team applied a mathematical watershed algorithm to the velocity field, the same kind of technique used in terrain analysis to define drainage basins in landscapes. Every galaxy flows downhill in the gravitational landscape. Trace where they flow, and you define the basin walls. Laniakea emerged as a single basin of enormous scale. The Milky Way sat inside it. The Great Attractor region, specifically the area centered on the Norma cluster, sat near Laniakea's gravitational core. The Shapley supercluster sat beyond the basin's far boundary, outside the defined structure, contributing its pull from outside. The implications took time to absorb. The Milky Way had always been inside Laniakea. The discovery was a new way of seeing a structure that had always existed, that had always contained us, that we had simply never identified as a coherent entity with a name. We had been living inside one of the largest known structures in the local universe without any awareness of it. Before Laniakea, the Milky Way's largest named context was the local group, about 60 galaxies spread across 10 million light-years. Zoom out, and we belong to the Virgo supercluster, a loosely defined collection of galaxy groups. Laniakea swallowed the Virgo supercluster and revealed it to be just one small piece of a vastly larger gravitational basin. It was like discovering your city, your country, and then the entire continent you had been living on, without ever having a name for it. The discovery received wide coverage. It gave people something concrete, a cosmic address: Milky Way, local group, Laniakea. A hierarchy placing our galaxy inside a structure 500 million light-years wide. But within the scientific community, something else in the data attracted attention that the public coverage largely skipped past. Laniakea was mapped. The velocity budget was substantially explained. Great Attractor plus Shapley together accounted for most of our 630 kilometers per second. Most, not all. Something contributing to our velocity had still not been identified. Something was missing from the picture. and the first hints of what it was pointed in a direction that no one had thought to look. The mathematics was clean. The result was not satisfying. After Laniakea, the velocity budget for the local group appeared largely accounted for. The Great Attractor region contributed a substantial fraction of our 630 km per second flow. The Shapley supercluster contributed nearly as much from its greater distance. Together, they explained the majority of the observed motion. Majority. The word carried weight. A residual remained. A few tens of kilometers per second, unaccounted for, persistent, showing up no matter how carefully the calculation was run. In cosmology, a few tens of kilometers per second is not noise. It is a signal. Yehuda Hoffman at the Hebrew University of Jerusalem led a team that took a different analytical approach to the cosmic flows. Two-velocity field. They applied a mathematical technique called Wiener filter reconstruction, which uses the observed peculiar velocities to infer the full underlying density field, including regions where observational data is sparse or missing entirely. The technique is designed to fill in the gravitational picture with the best possible estimate given what is actually measured. The reconstruction revealed something the standard approach had missed: the Wiener filter. Reconstruction found no new attractor, no new massive cluster in some unmapped corner of the sky. What it found pulled attention through its absence. A region of space with significantly less matter than the cosmic average. A void, large, deep, located in a direction roughly opposite to the Great Attractor. If the Great Attractor pulls us toward it from one side, a void on the other side would push us away from that direction, adding to our net velocity toward the attractor. Two mechanisms. One, observed motion. The void was pushing nearly as much as the attractor was pulling. Astronomers had been searching for missing mass to explain the residual velocity. The answer was not mass at all. It was the absence of mass. This inverted the mental model that had shaped the field for decades. The attractor story had always been a story about things that pull, heavy objects, dense clusters, massive superclusters. The question had always been, what is massive enough to pull us this hard? That framing assumed the motion was entirely the product of attraction toward high-density regions. It was half right. The other half of our velocity comes from being pushed away from a region that is emptier than average. The direction the local group moves is shaped both by what lies ahead and by what does not lie behind. That void had been hiding in the data, visible only when the full velocity field was reconstructed with enough precision and sophistication to bring it out. It would receive its own name. And once researchers understood that the motion budget required both an attractor and a repeller, the framework for understanding where we are going changed entirely. The Great Attractor story was not finished. It had just become something more layered, more complete, and considerably harder to reduce to simple terms. What comes next requires sitting with a new and unsettling idea. That emptiness, too, has gravitational power over where we go. The idea seemed complete. Shapley pulled, gravity pulled. That was the story astronomers told for decades. But in 2017, a team led by Yehuda Hoffman at Hebrew University published something that changed the picture entirely. They changed it not by finding more mass. They changed it by finding less. They called it the dipole repeller. Almost exactly opposite the Shapley supercluster in the sky sits a vast region containing far fewer galaxies than average, far fewer clusters, far fewer of anything. A cosmic void stretching roughly 700 to 740 million light-years from here. Not a region where galaxies fell into clusters. A region left behind while everything around it clumped together over billions of years. And that emptiness, it turns out, has consequences nobody fully appreciated until Hoffman's team did the calculation. Think about gravity differently for a moment. Mass pulls things toward it, but in a universe where the average density of matter creates a background pull in all directions, a region with far less than average becomes a gravitational low point. Things drain away from it. They move toward higher density regions, and that drainage, seen from outside, looks exactly like a push. The Milky Way is moving away from the dipole repeller. Hoffman's confirmed finding was stark. The repulsion from this void contributes roughly as much to our total velocity through space as the attraction from the Shapley supercluster. We had measured our cosmic motion for decades and attributed most of it to mass pulling us in. This team showed we had the picture half wrong. About half of our 600 kilometers per second velocity comes not from attraction. It comes from repulsion, from nothing. The result was published in Nature Astronomy in 2017. It stands as confirmed science. It demands a change in how we think about gravity's role in the universe. Gravity has always been framed around what is there: mass, density, concentration. But the universe is not uniform. Some regions hold vastly more than average, some hold vastly less. And the contrast between them, that gap between the full and the empty, that contrast is what actually steers galaxies across billions of light years. We are not just falling toward Shapley, we are also fleeing the void. Half our cosmic velocity, half the speed at which the Milky Way drifts through its large-scale environment, generated by a region containing almost nothing. No single massive attractor, no dramatic concentration of matter, just absence. Stretched across hundreds of millions of light years, the void does not need to actively push, it just needs to exist. Mass elsewhere creates higher gravitational potential. Matter flows toward it. The regions left behind become gravitational deficits. They push by default, passively, continuously. Without a visible source you can point to on any map, this reshaped how cosmologists model our motion through the universe. It changed every accounting of the forces shaping where we go. And it raised a question that had never been asked quite so directly. If a void that size, that far away, contributes that much to our speed through space, what else might we be missing? The answer came faster than expected, and it came not from empty space. It came from behind a wall of dust and gas so thick that what lay behind it was, until very recently, almost entirely unknown. The wall in question is called the zone of avoidance. It is not metaphorical. Our own galaxy, the Milky Way, stretches across the sky as a dense band of stars, gas, and dust. Telescopes looking through that band see almost nothing beyond it, because the dust absorbs and scatters light. Most of the universe behind our own galactic plane has been hidden from optical view since the beginning of modern astronomy. Astronomers knew this was a problem. They worked around it. Infrared telescopes penetrate dust better than optical ones. Radio telescopes better still. By the early 2000s, most astronomers had come to believe the broad strokes of the picture were filled in. Perhaps some smaller structures remained undiscovered, but no one expected another Shapley hiding in the dark. In 2016 and 2017, René Kraan-Korteweg at the University of Cape Town decided that was not good enough. Using the AA Omega multifiber spectrograph and the Southern African Large Telescope, her team gathered 4,500 new galaxy redshifts in the zone of avoidance. 4,500 new data points from a region most surveys had treated as effectively blank. What they found stopped the field. A supercluster, a full supercluster comparable in mass to the Shapley supercluster, sitting roughly 800 million light-years away, stretching somewhere between 320 and 400 million light-years across. It had been right there, behind our own galaxy's disk, and nobody had known it existed. They named it the Vela supercluster. The name comes from the constellation Vela in the southern sky. The structure lies partially hidden behind the galactic plane and partially scattered across a region that previous surveys had simply not penetrated deeply enough to see. The structure was not a small cluster. It was comparable to one of the most massive known concentrations of galaxies in the nearby universe, and it had been invisible to us. This is a confirmed discovery, published in 2017 in the monthly notices of the Royal Astronomical Society. The mass of the Vela supercluster means it exerts gravitational influence on the motion of galaxies in its neighborhood, including, potentially, our own. How much it contributes to our velocity is still being worked out. Scientists consider this an active area of research. Early estimates suggest it may add several dozen kilometers per second to our motion, pulling the Milky Way in a direction that partly overlaps the combined pull from Shapley and the repulsion from the dipole repeller. We had spent decades building a map of the large-scale gravitational landscape around us, and hiding in the one place our telescopes could not easily look sat a structure we never counted. That matters for more than academic reasons. Every model of how our galaxy moves, every calculation of where we are going and how fast, had been built without accounting for the Vela supercluster. The models were incomplete. The map was wrong. But here is the part that should give you pause. Vela was not the last surprise hiding in the zone of avoidance. It was not even close to the last. Because behind that wall of dust and gas, something far stranger has been accumulating, and the telescope that found it changed what we thought we knew about our own blind spots. After the Vela supercluster, the obvious question was, what else is back there? The zone of avoidance covers roughly 20% of the sky, 20% of our observable universe, at least in terms of angular coverage, had been effectively blacked out by our own galaxy. Infrared surveys had revealed some of what lay behind it. Radio surveys had done the same. By the early 2000s, most astronomers had come to believe the major structures were accounted for. Perhaps smaller features remained undiscovered, but no one expected another Shapley-scale object hiding behind the dust. Vela proved that assumption wrong. Since 2017, a radio array in South Africa called Meerkat has been running what are called 21-centimeter hydrogen-blind surveys through the zone of avoidance. Meerkat consists of 64 radio dishes spread across the Karoo Desert, operating together as a single instrument of extraordinary sensitivity. At 21 centimeters, radio waves pass through the dust of the galactic plane with almost no absorption. The telescope does not need to see around the wall. It sees straight through it, and what it sees keeps coming. Hundreds of previously unknown galaxies have been catalogued in just the first years of Meerkat operations. Full galaxies, many of them in groupings and filaments, hinting at larger structures waiting to be mapped. The surveys are ongoing. Each new data release extends the list rather than completing it. Here is what makes this genuinely unsettling for our models. The zone of avoidance was not supposed to contain surprises at this scale anymore. Infrared satellite surveys had been looking through it for decades. Astronomers corrected their models. The scientific consensus heading into the 2010s was that while the zone of avoidance still hid details, the major structures were accounted for. The Vela supercluster, discovered in 2017, comparable in mass to Shapley, had not been accounted for, not even approximately, and Meerkat is finding that Vela may not be alone. The structures Meerkat is tracing behind the galactic plane are not yet fully mapped. Data resolution and survey coverage are still growing. Researchers working on this consider most conclusions about newly found structures preliminary. This is honest science in motion, but the direction of discovery is unmistakable. Every new look behind the wall finds more than the look before it found. That pattern should make anyone asking about our cosmic motion very uncomfortable, because every new mass discovered behind the zone of avoidance is mass we had not accounted for in our gravitational models. Mass that may be pulling on us, steering us, contributing to a velocity we thought we mostly understood. We thought we had mapped the forces shaping where the Milky Way goes. We had mapped the part of the sky we could see easily. The rest, 20% of the sky, was still giving up its secrets as recently as 2023. And the zone of avoidance was not the most unsettling blind spot in this story. That distinction belongs to a signal nobody could agree was real. In 2008, a NASA astrophysicist named Alexander Kashlinsky published a paper that made the scientific community deeply uncomfortable. He did not discover a new supercluster. He did not find a hidden void. He claimed to have detected something far more radical, a motion, a drift, shared by thousands of galaxy clusters across billions of light years, all moving coherently in the same direction. He called it dark flow. The claim was specific. Using data from NASA's WMAP satellite, Kashlinsky and his team measured something called the kinematic Sunyaev-Zeldovich effect. When photons from the cosmic microwave background pass through the hot gas in a galaxy cluster, they get a slight energy boost from the electrons moving relative to the photons. The size of that boost depends on how fast the cluster is moving and in which direction. By measuring this signal across hundreds, then thousands of clusters, Kashlinsky's team built a velocity map. What they found was not random. Thousands of clusters, spread across an enormous swath of sky, all showed a coherent drift of between 600 and 1,000 kilometers per second in the same general direction. Not local, not caused by anything we could see in our observable universe. Coherent motion stretching out to distances of several billion light years. If that signal was real, the implications would rewrite cosmology. Standard cosmological models predict that at very large scales, the motions of galaxy clusters should be essentially random. The universe should look the same in all directions far enough out. Coherent bulk motion of that magnitude, at that scale, is not what the standard model expects. Kashlinsky's interpretation was direct. The signal pointed to gravitational influence from structure outside the observable universe. Structures beyond the cosmic horizon, never to be directly seen, massive enough to drag thousands of clusters in a single direction across the portion of space we can observe. Structure beyond the observable universe, pulling on us. The scientific community did not embrace this. The reception was skeptical, vocally, persistently skeptical. The methodology was questioned. The statistical approach was challenged. The effect size seemed too large. Alternative explanations, from foreground contamination to systematic errors in the WMAP data itself, seemed more plausible to many researchers than the idea that something beyond our horizon was steering galaxy clusters. But the data would not disappear. Kashlinsky and his collaborators refined their analysis over the following years. They extended it to more clusters. They published follow-up papers in 2010 and 2012. Each time, the signal persisted. The direction remained consistent. The amplitude stayed in the same range. The debate was not resolved by better arguments. It was suspended, awaiting better data. Better data was already in orbit. The European Space Agency's Planck satellite launched in 2009 with the explicit goal of mapping the cosmic microwave background at higher precision than any previous instrument. Higher resolution, better sensitivity, more frequency channels to separate foreground contamination from the true signal. Planck had the tools to either confirm dark flow or bury it. The results, when they came, seemed to deliver a verdict. The scientific community largely accepted that verdict. Kashlinsky did not, and the story did not end there. The Planck satellite was designed to be the definitive word on the cosmic microwave background. Launched in 2009 by the European Space Agency, it spent 4 years mapping the faint radiation left over from the early universe with extraordinary precision, 30 times more sensitive than WMAP in some frequency channels. 9 frequency bands against WMAP's 5, a map so detailed that when researchers published the first full results in 2013, it reshaped entire fields of cosmology. One of the things Planck was expected to settle was dark flow. The Planck analysis team published their findings across several papers between 2013 and 2016. Their conclusion was direct. They found no statistically significant dark flow signal. The upper limits they placed on any coherent bulk motion fell far below Kashlinsky's claimed 600 to 1,000 kilometers per second. Planck's more precise frequency coverage allowed researchers to better separate foreground dust emission and other contaminants that critics had always suspected were polluting WMAP's measurements. The scientific community broadly accepted Planck's verdict. Dark flow, as Kashlinsky had described it, was most likely a methodological artifact, a contamination problem dressed up as a signal. The extraordinary claim had failed the test of extraordinary evidence. Kashlinsky disagreed. He published responses arguing that the two analyses were not directly comparable, that the cluster samples differed, that the Planck team's own methodology had its own limitations. He maintained that the WMAP signal was real and that Planck's analysis did not cleanly contradict it so much as fail to replicate it using different methods on a different sample. This remains a contested point in the technical literature. The disagreement was not resolved by concession. It was buried under the weight of community consensus. And community consensus has a history, in cosmology especially, of being revised. Here is what deserves careful attention. Planck's result is a partial rebuttal, not a complete one. The satellite found no significant signal in its own data. It did not prove Kashlinsky's data wrong. It provided a null result at higher precision, and the community interpreted that as a refutation of the original claim. That interpretation is reasonable. It is also the kind of reasoning that occasionally turns out to be premature. The scientific consensus today holds that dark flow is not an established phenomenon. It is not in the textbooks. It is not included in standard models of large-scale structure. Most researchers working in this area consider the question settled. But Kashlinsky kept working, he kept analyzing, he kept publishing, and the bulk flow measurements being collected by entirely different surveys, using entirely different methods, had a habit of turning up results that looked a great deal like what he had been claiming all along. The question was put to rest, and then the universe declined to let it stay there, because in 2023, a survey of nearly 56,000 galaxies produced a result that reopened the anomalous bulk flow question, reopened it loudly. And this time, the data came from a source no one could easily dismiss: cosmic flows. 4 was not a radical project by design. It was a catalogue. A patient, methodical accumulation of galaxy distance measurements gathered over years by a collaboration of astronomers mapping how galaxies move relative to the smooth expansion of the universe. The 4th iteration, released in 2023, contained 55,877 galaxy distance measurements, the largest catalogue of its kind ever assembled. The intention was straightforward: map galaxy velocities at different distances, compare them to what the standard cosmological model predicts, check for agreement, refine the picture. The picture did not cooperate. At scales of roughly 150 to 200 megaparsecs, which translates to roughly 500 to 650 million light-years. The cosmic flows. 4 catalog finds bulk flows, coherent motions of galaxies moving together through space, beyond what the smooth expansion of the universe explains. The measured speed of those flows falls between 380 and 430 kilometers per second. The standard cosmological model, the one called lambda CDM, that physicists and cosmologists use as their benchmark for understanding the large-scale universe, predicts bulk flows at those distances of roughly 140 kilometers per second. The difference is not small, 3 times larger than predicted. At some scales, the probability of getting a cosmic flows 4 result under the standard model is approximately 1 in 650,000. In scientific terms, that sits between 3 and 6 sigma. A result in that range does not get ignored. The debate is not settled. The Cosmic Flows 4 team itself, led by Brent Tully at the University of Hawaii, acknowledges the anomaly. Researchers have proposed several explanations. Systematic errors in the distance measurements are one candidate. Distance measurements in astronomy are notoriously difficult to make precisely, and at the scales Cosmic Flows 4 is probing, Small, systematic biases can compound into apparently large signal. Other researchers argue that the peculiar velocity field at these scales is genuinely anomalous and reflects real physics not captured in the standard model. No consensus has formed. This remains an active, unresolved debate, but here is what makes this anomaly sit differently than previous ones. The Cosmic Flows program has been accumulating data for years. The methodology is well understood. The team has published multiple catalog versions before this one. The result did not come from a novel, untested technique. It is the latest and most precise result from a long-running, respected project. And the anomaly grew larger as the sample grew larger. More data made the signal stronger, not weaker. That is not what you want to see if you're hoping for a statistical fluke. Statistical flukes generally shrink as you add more measurements. Real signals hold. If the cosmic flows, for bulk flow is real. If the universe around us contains coherent galaxy motions 3 times larger than our best model predicts, then either our model is missing something significant about the matter distribution around us, or there is physics operating at these scales that we have not yet understood. Either possibility would require rethinking what is pulling and pushing the Milky Way. And cosmic flows, 4 was not the only measurement pointing in that direction. There is a number at the center of everything we think we know about our cosmic motion, 630 kilometers per second. That is the speed at which the Milky Way moves through the cosmic microwave background reference frame, not relative to a local galaxy or nearby cluster. Relative to the oldest light in the universe, the background radiation filling all of space, left over from the earliest moments after the Big Bang. We measure this using what is called the CMB dipole. The radiation is slightly warmer in one direction and slightly cooler in the exact opposite direction. The pattern arises because the Milky Way is moving toward the warmer side. The size of the temperature difference tells us our speed. The direction tells us where we're headed, 630 kilometers per second toward the Hydra Centaurus constellation. This measurement is one of the most precise and reliable in all of cosmology. The direction and speed have been confirmed by multiple satellites, multiple analysis teams, and decades of work. The CMB dipole is not debated. What is debated is what it actually means. There is another way to measure our motion through the universe. You can look at the distribution of distant galaxies, quasars, and radio sources across the sky. Because we are moving, we should see a slight excess of objects in the direction we're heading and a slight deficit behind us due to aberration and Doppler effects. This is called the matter dipole, or the radio dipole. Under the standard model, it should point in the same direction and match the same speed as the CMB dipole. It does not. Multiple independent surveys of radio galaxies and quasars find a matter dipole roughly twice as large as the CMB dipole. The direction is close, but not identical. The discrepancy sits between 3 and 5 sigma, depending on which survey you analyze and which method you apply. It has been found in the NRAO VLA Sky survey data, in the Catwise Quasar Catalog, and in multiple subsequent analyses published between 2020 and 2023. At 3 to 5 sigma, the signal is not a whisper, it is a shout. The scientific community has not agreed on what it means. One possibility is that the CMB dipole has a component that is not purely kinematic, that some fraction of the temperature asymmetry in the ancient radiation has a different cause, possibly related to an intrinsic asymmetry built into the early universe. If that is true, the CMB dipole does not perfectly encode our motion. Another possibility is that the universe is not perfectly isotropic at the largest scales, that the distribution of matter is genuinely different in different directions, even at the distances where we expect things to smooth out. This would challenge the cosmological principle, the foundational assumption that the universe looks the same in all directions at large scales. Both possibilities are serious. Either would require changes to our standard picture of cosmology. Neither is resolved. two measurements of the same physical thing give two completely different answers. One is twice the size of the other. Both are well constructed. Both are published in peer-reviewed literature. And no one has a clean, agreed-upon explanation for why they disagree. That is where the field stands right now. And it brings us to the question of structure itself. Because to understand the forces shaping our motion, you first have to understand the architecture underneath everything. To understand why we move the way we do, you have to understand what the universe is built from. The position of galaxies is only part of it. The scaffolding beneath them matters more. The architecture underneath everything visible, cosmologists call it the cosmic web, and it is exactly what it sounds like. The universe, on the largest scales we can observe, is not filled with galaxies scattered evenly in all directions. It is organized into a network of filaments. Long threads of matter, hundreds of millions of light years in length, dense with galaxies, connected at intersections called nodes. Between the filaments stretch vast, empty regions called voids. The whole structure looks, in simulation, strikingly like a three-dimensional web. Each filament connects to others. Each node is a cluster or supercluster where multiple filaments meet. Shapley is a node, one of the most massive nodes in our observable neighborhood, a place where multiple filaments converge and an enormous concentration of matter accumulates. The dipole repeller is a void, a space between the threads where matter is sparse and gravity drains outward in all directions. Laniakea is a basin, a region where galaxy velocities, corrected for the expansion of the universe, flow inward toward a common low point. Our supercluster's shape is defined by the flow of matter through the web. This structure did not arise by chance. It was seeded by quantum fluctuations in the very early universe, fluctuations so small they were genuinely quantum in origin. Those fluctuations became slight overdensities in the distribution of matter. Gravity amplified them over billions of years. Matter fell toward the overdensities, creating filaments. The densest intersections became clusters and superclusters. The regions between them emptied into voids. And most of the matter doing this work is invisible. Dark matter comprises roughly 80 to 85% of the total matter content of galaxy clusters. It does not emit light. It does not interact with light. We cannot see it directly. We infer its existence from its gravitational effects on the matter we can see. In the cosmic web, dark matter forms the actual skeleton. The filaments, the nodes, the overall architecture are primarily dark matter. Ordinary matter, the kind making stars and gas and planets and us, falls into the gravitational wells carved by dark matter and accumulates there. We are being pulled and pushed by something we cannot see, towards something we cannot fully observe, through a structure built primarily from matter we cannot detect directly. The Shapley supercluster pulling us is mostly dark. The dipole repeller void pushing us is defined by the absence of mostly invisible matter. The Vela supercluster behind our galactic plane is a concentration of dark matter with visible matter tracing its outline. Laniakea itself is a gravitational basin carved by the unseen. Every force steering the Milky Way through space is dominated by something that appears on no light-based map of the universe. The caveat is not small. It is the central fact of our motion. We are moving through a universe we can see only partially, steered by forces we can only infer, toward a destination defined by structures we are still in the process of discovering. And the discoveries keep coming, because even our address in this web has turned out to be wrong. Every few decades, astronomers have to update humanity's cosmic address. For most of human history, Earth was the center of everything. Then it became one planet around one star. Then one star in one galaxy, then one galaxy in a local group, then a local group inside a supercluster. The supercluster used to be the end of the story. The Virgo supercluster, our home, roughly 110 million light-years across, named for the Virgo cluster at its heart. For much of the late 20th century, that was the answer to where we live in the universe. In 2014, a team led by Brent Tully at the University of Hawaii redrew the boundary. They used galaxy flow data to define superclusters, not by arbitrary proximity, but by actual gravitational watersheds. Wherever galaxy velocities converge toward a common point, that region defines a basin, a supercluster, a home. By that definition, the Virgo supercluster is not our home. It is a small tendril of something much larger. Our true supercluster is Laniakea, 520 million light-years across, containing roughly 100,000 galaxies with a total mass of roughly 100 million billion times the mass of our star, nearly 5 times the size of the Virgo supercluster. Laniakea became our new cosmic address. It lasted less than a decade before that address started to wobble. A study, published in 2024, looked carefully at the relationship between Laniakea and the cosmic addressness. Shapley supercluster. Shapley sits roughly 650 million light-years away. It was always understood to be a powerful gravitational influence on our motion. It was also understood to be a separate structure, a neighbor, an external source of pull. The 2024 analysis found something different. Using updated velocity field data, it estimated roughly a 60% probability that Laniakea is not an independent supercluster sitting beside Shapley. Instead, Laniakea may be a sub-basin of Shapley itself, a tributary within a larger watershed, a suburb of a city we thought was a separate country. The finding is not confirmed. 60% probability reflects genuine uncertainty, and researchers working on this question consider it unresolved. Different analysis methods give different answers depending on how you define the boundaries between gravitational basins at these scales. But if it holds up, the implications are direct. Shapley may not be just a massive neighbor pulling us toward it. It may be the larger structure we already live inside. The attractor we are falling toward may be our own home's organizing center. Our cosmic address would need to change again, and the pattern this story keeps revealing. Each decade, the map gets redrawn. Each revision makes Earth a smaller piece of something larger. Is not an accident, it is a trend. Every tool we build sees farther. Every survey we run finds more. Every structure we map turns out to sit inside something we had not yet measured. The address keeps revising in one direction only, outward, towards something bigger and less comprehensible. And then there is the structure at the farthest edge of what any survey has ever reached. The one that should not exist. The one that puts everything else in this story into a different perspective entirely. Everything described so far sits within a few billion light-years of Earth. The Shapley supercluster at 650 million light-years. The dipole repeller at 730 million. The Vela supercluster at 800 million. Laniakea spanning 520 million. These are enormous distances by any human measure. But they are local, fitting inside a small fraction of the observable universe, which stretches nearly 46 billion light-years in every direction. At the largest scales, the standard cosmological model makes a clear prediction. The universe should be smooth, homogeneous. Structures that exist at smaller scales should average out above roughly 1.2 billion light-years. You should not find coherent structures larger than that, because the physics of the early universe, the way matter was distributed after the Big Bang, does not leave room for them. This is called the cosmological principle, the foundational assumption that the universe, on the largest scales, looks the same in every direction. In 2013, a group of researchers found something that challenges it directly. They were not mapping galaxies, they were mapping gamma-ray bursts, the most energetic explosions in the universe. Brief flashes of radiation so bright they can be detected billions of light-years away. Gamma-ray bursts are useful as cosmic tracers precisely because they are visible across enormous distances. A team led by Attila Horvath at the Konkoly Observatory in Hungary analyzed the statistical clustering of gamma-ray bursts and found a concentration associated with the Hercules and Corona Borealis constellations. The Hercules Corona Borealis Great Wall. The team estimated its size at roughly 10 billion light-years across, roughly 10% of the entire diameter of the observable universe. It would be the largest known structure in the universe, and under the cosmological principle, it should not exist. This result remains debated. The detection method, statistical clustering of gamma-ray burst positions, is not as direct as mapping galaxy redshift. Gamma-ray bursts are rare and distributed unevenly across time, making a complete and unbiased spatial map difficult to construct. Some researchers question whether the apparent structure reflects a real physical concentration or an artifact of the detection catalog. The Hercules Corona Borealis Great Wall has not been confirmed to the same standard as Shapley or the dipole repeller. The scientific community considers it a serious candidate structure, not an established fact, but serious is the operative word. A structure at this scale, if real, cannot be explained by current theory. And here is where everything in this story converges on something almost too large to hold in mind. We are a planet orbiting a star in the Milky Way. The Milky Way sits in Laniakea, which may itself sit inside Shapley. Shapley is a node in a cosmic web mostly built from invisible matter. The dipole repeller pushes us from one side, while Shapley pulls from the other. The zone of avoidance still hides structures. The CMB dipole and the matter dipole disagree by a factor of 2 with no agreed explanation. Bulk flows measured by cosmic flows 4 exceed standard model predictions by 3 times. And at the farthest scales ever probed, a structure 10 billion light-years wide challenges the assumption that the universe is smooth. If the universe contains structures we cannot explain at its largest scales, then the question of what is pulling the Milky Way is no longer just a question about local gravity. It has entered a completely different dimension of the unknown. The model was supposed to be finished. Lambda CDM, lambda cold dark matter, the standard cosmological model. For 25 years, it has been the foundation of everything we think we know about the universe: how galaxies form, how matter clumps, how structure emerges from the chaos of the early universe. It was tested, confirmed, and celebrated. Cosmologists called it the concordance model because so much data pointed to the same answer. But concordance is not unanimity, and lately the cracks are getting harder to ignore. Start with cosmic flows. 4. The bulk flows it measured, the large-scale streaming motions of thousands of galaxies, came in at roughly 3 times larger than lambda CDM predicts. 3 times. That is not a measurement error or a rounding difference. That is the model and reality telling different stories in a loud public way. Now add the dipole mismatch, the CMB dipole, the slight temperature variation in the cosmic microwave background caused by Earth's motion points in one direction. The matter dipole, derived from counting distant galaxies, points in a slightly different direction. They should agree. Under lambda CDM, they must agree. They do not. Cosmologists debate the magnitude of the discrepancy, but several independent analyses have confirmed that something is off. Now add the Hercules Corona Borealis Great Wall. This structure is enormous, 10 billion light-years across by some estimates. Lambda CDM places strict limits on how large cosmic structures can be. The universe, it says, should be smooth at the largest scales. Structures beyond about 1 billion light-years should not exist as coherent features. The Hercules Corona Borealis Great Wall violates that limit by an order of magnitude. Some researchers dispute whether it is truly a single structure, but the dispute itself signals trouble. Now add dark flow, the claim that galaxy clusters appear to stream in a coherent direction beyond what known mass can explain. Planck's team said the signal was noise. Koszlinski's team said Planck misread the method. The argument has not been resolved. The signal has not disappeared. Each of these anomalies, considered alone, has an explanation. Measurement error, selection bias, statistical fluctuation. The scientific community is rightly cautious about any one anomaly. A single strange result is a single strange result, but 4 anomalies, independent of each other, all pointing toward the same conclusion: that the universe is less smooth, less uniform, and less well described at the largest scales than lambda CDM predicts. That is a different situation entirely. Several cosmologists have now said publicly what used to be whispered in conference hallways. The standard model is not broken, but it may be incomplete. There may be physics operating at the largest scales that the current framework simply does not account for. This matters for a reason that connects directly to everything in this story: the motion of the Milky Way. Our galaxy's 600 km/s fall towards something we cannot fully see was supposed to be explained by lambda CDM, the Great Attractor, the Shapley concentration, known structures, known physics, known math. But if the model is cracking at the edges, then the sources of that motion may not be fully known. The pull we feel may not be fully explained, and what remains unexplained may require something beyond the framework that has guided cosmology for a generation. That possibility used to be unthinkable. It is no longer unthinkable. It is the subject of papers, conferences, and careers. 1998 changed everything. 2 independent research teams were measuring the brightness of distant supernovae, type Ia supernovae, stellar explosions so consistent in their peak luminosity that they serve as standard candles across cosmic distances. By comparing how bright they appear against how bright they should be, astronomers can calculate how fast the universe was expanding at different points in its history. Both teams expected to find that expansion was slowing down. Gravity was supposed to be doing what gravity does, pulling matter together, gradually decelerating the outward momentum of the Big Bang. Instead, they found the opposite. Expansion was speeding up. The universe is accelerating outward. Something is pushing space itself apart, and that something is winning against gravity on the largest scales. The teams shared a Nobel Prize in 2011. The finding is not debated. It is confirmed physics. The acceleration is real. The name given to whatever is causing this is dark energy. It does not heat anything. It does not radiate. It cannot be detected directly. It is a mathematical placeholder for an observed effect, and by the best current measurements, it accounts for roughly 68% of the total energy content of the universe. Ordinary matter, everything you can see, touch, and weigh, accounts for about 5%. Dark matter about 27%. Dark energy, 68%. Now here is what dark energy does to our story. The Milky Way is falling toward the Great Attractor, a region of concentrated mass roughly 150 million light-years away. Beyond it, the Shapley concentration pulls from about 650 million light-years out. Our galaxy moves toward them at hundreds of kilometers per second. That motion is real, it is measured, it is not going to stop. But the space between us and those structures is also expanding. Because of dark energy, that expansion is accelerating in what cosmologists call co-moving coordinates, the framework that accounts for expansion. The Great Attractor and Shapley are actually moving away from us, even as we fall toward them. The Milky Way is chasing a target that is, in the deepest physical sense, running away. For now, gravity still dominates at these scales. The pull is real enough that we have a genuine, peculiar velocity, motion beyond what expansion alone would produce. But at greater distances, and over longer timescales, expansion wins. Dark energy operates uniformly across all of space. It does not negotiate with the gravitational attractions of individual superclusters. The mathematical consequence is this: we will never arrive at the Great Attractor. We will never reach Shapley. The fall continues indefinitely, but the destination keeps receding faster than we can close the gap. This is confirmed. This is a direct consequence of measured expansion rates and the equations that govern them. We are in permanent freefall toward a horizon that the universe guarantees we can never cross. In 2014, a team of cosmologists drew a map using the peculiar velocities of over 8,000 galaxies from the Cosmic Flows 2 dataset. They traced gravitational basins across the local universe. A gravitational basin works like a watershed. Rain on one side of a mountain drains to one river. Rain on the other side drains to another. Galaxies inside a gravitational basin all flow toward a common attractor. They found a basin of extraordinary scale. The Milky Way, the Virgo cluster, the Great Attractor region, and thousands of other galaxies all belong to a single gravitational watershed. The team named it Laniakea. In Hawaiian, the word means immeasurable heaven. It stretches roughly 500 million light-years across and contains the mass equivalent of 100 million billion stars. It sounds permanent. It is not. Laniakea is not gravitationally bound. This is the distinction that gets lost in almost every popular account, and it matters enormously. A gravitationally bound system, like the Milky Way itself, or the local group, will stay together. Gravity holds it through any expansion. But Laniakea is a flow pattern, not a bound structure. It describes where things are currently moving, not a configuration that will last. Dark energy will take it apart. Over tens of billions of years, accelerating expansion will overcome the gravitational tendencies that currently define Laniakea's basin. The outer edges will begin to drift away. The inflow that today characterizes the basin will slow, then reverse in the outermost regions, as expansion outpaces the gentle gravitational gradient. What is now a coherent watershed will fracture into disconnected islands of locally bound mass. The Great Attractor region itself may fragment. The clusters that make it up are already moving, merging, evolving. On these timescales, the structure we have been falling toward will not exist in its current form. Compare this to something closer to home. In roughly 4.5 billion years, the Milky Way and Andromeda will collide. That is confirmed. Gravity has already sealed that fate. The two galaxies are moving toward each other fast enough that no amount of dark energy will prevent the encounter. The merger will happen. It is local, it is bound, and it is certain. The fall toward the Great Attractor is different in kind. Local bound systems will survive. The larger flow patterns will not. Laniakea, as a structure, has an end date written into the physics of the universe. So the Milky Way falls toward a center that is itself dissolving. We are passengers in a river that is drying up even as we move downstream. The destination has an expiration date we will never live to witness. The fall is permanent, the arrival is impossible, and even the attractor will not last. The universe offers no fixed points at these scales. Only motion, only change, only the quiet certainty that everything, eventually, will drift beyond everything else. Here is a question that sounds simple and turns out to be one of the hardest in observational cosmology. How far out do you have to look to fully explain the Milky Way's motion? The technical term is convergence depth. It refers to the distance at which, once you have accounted for all the mass within that radius, the gravitational math closes. The numbers add up. The peculiar velocity is fully explained. You stop looking because there is nothing left to find. In the early 1990s, the first models suggested convergence at roughly 100 to 150 million light-years. That would mean the Great Attractor region and its immediate surroundings were sufficient. Map everything within that shell, run the gravitational equations, and you would recover the Milky Way's observed motion. Then better data arrived. The PSCZ survey, the 2-micron all-sky survey. Each expanded the reach of peculiar velocity measurements, and each pushed the convergence depth farther out. The Shapley concentration, sitting at roughly 650 million light-years, was found to contribute meaningfully to our motion, not marginally. Meaningfully. cosmic flows, 4 pushed the estimated convergence depth to over 300 million light-years in its primary analysis. But the Shapley contribution persists even beyond that, 300 million light-years of survey depth, and the numbers still do not fully close. Every time the reach of measurement increases, the source of our motion retreats. There are 2 ways to read this pattern. The first is optimistic. Maybe convergence is real, but distant. Once surveys reach deep enough, the accounting will close. All the mass responsible for our motion exists somewhere we have not yet fully mapped, and with patience and better instruments, we will find it. The problem is measurement depth, not physics. The second interpretation is more unsettling. Maybe convergence keeps retreating because there are gravitational sources beyond any depth we can ever reach. The zone of avoidance still hides significant sky area behind the disk of our own galaxy. The deep universe still contains structures we have not catalogued, and at the theoretical limit, there is the cosmic horizon itself, the edge of the observable universe, beyond which no signal can ever reach us. If mass beyond that horizon is pulling us, convergence will never be found. Not because we lack the technology, because the universe does not allow observation past that point. Several researchers have noted that the behavior of bulk flow measurements, their persistence at increasing depths, their consistent direction, is exactly what you would expect from a source that lies beyond our observational horizon. The signal does not weaken the way it should if all the sources are within reach. The convergence problem does not confirm dark flow, but it does tell us something honest about the limits of any model that relies only on what we can see. The mass budget explaining the Milky Way's motion may not be fully local, it may not be fully visible, and the final accounting may require looking somewhere that no instrument will ever reach. Alexander Kashlinsky first published the dark flow signal in 2008. The claim was specific, using X-ray data from galaxy clusters and cross-referencing it against the cosmic microwave background. His team detected a coherent bulk motion of clusters across a volume of space far too large to be explained by known gravitational sources, hundreds of millions of light-years, possibly more, all streaming in the same direction. He called it dark flow. The scientific community was skeptical from the beginning. The signal was subtle. The method was technically demanding. The implications were extraordinary. In 2013, the Planck satellite released its own analysis of the same signal. Planck found no statistically significant dark flow. The European Space Agency's flagship cosmic microwave background mission, with its exquisite sensitivity and full sky coverage, looked where Kashlinsky looked and did not find what Kashlinsky found. Most researchers took that as the end of the argument. Kashlinsky did not concede. His response was methodological. He argued, in detailed follow-up papers with his collaborator, Fernando Atrio-Barandella, that the Planck team had misapplied the kinematic Sunyaev-Zeldovich technique at the core of the method. The filtering choices differed. The cluster weighting differed. The teams were not, Kashlinsky argued, running the same test. They were testing different things and comparing the results as if they were equivalent. He continued publishing. In subsequent analyses, he and Atrio-Barandella showed that when the original method is applied correctly to Planck's own data, a statistically significant dipole signal persists. The signal did not disappear when examined with more sensitive instruments. It changed depending on how those instruments' data were handled. The situation is not comfortable for science. Both teams are rigorous. Both are using real data. They arrive at different answers, and neither side has found the specific error in the other's work that would settle the matter definitively. Kashlinsky is now developing an instrument called NIRBADE, Near-Infrared Background Anisotropy and Dipole Experiment, designed for the European Space Agency's Euclid satellite, which launched in 2023. NIRBADE would test the dark flow hypothesis through an entirely independent channel, the near-infrared background, rather than cluster microwave data, a different signal, a different method. The same underlying question, That instrument has not yet delivered results. The test is coming. What makes this worth sitting with is what it reveals about how science actually operates. Science is often presented as a clean sequence: question, measurement, answer. Dark flow is something else. It is science as a sustained, contested, unresolved argument between serious people with serious data. The community has not confirmed dark flow. It has also not proven it wrong. It has arrived at an uncomfortable middle ground, the kind that does not make headlines, but does make cosmologists lose sleep. Koszaliński has been defending this argument for 18 years. That kind of sustained, methodologically precise dissent is not noise. It is how science eventually finds what it missed, or rules out what it cannot confirm. Either way, the near-bade results will move the needle when they come. There is a wall we cannot see through, not a wall of matter or energy, a wall of time. The observable universe stretches about 46 billion light-years in every direction. Beyond that boundary, the universe continues, possibly forever, but no light, no signal, and no information of any kind has had time to reach us in the 13.8 billion years since the Big Bang. What lies beyond is, by definition, permanently inaccessible to direct observation. The limit here is not technological, it is a limit of physics itself. Now return to dark flow. If Koszaliński's signal is real, and it has not been ruled out, the most straightforward explanation involves gravitational attraction from structures that lie beyond that boundary. In the framework of cosmic inflation, the universe in its earliest moments expanded at a rate that could place enormous concentrations of mass energy outside our observable horizon. Inflation happened fast and spread regions of space so rapidly that what began as quantum fluctuations became the seeds of structure at scales we cannot calculate with certainty. Some inflationary models predict that regions of higher than average density could exist just beyond our horizon, massive enough to pull gravitationally on structures near the edge of what we can observe. This remains debated. Many physicists consider gravitational influence from beyond the horizon to be untestable by any conceivable method, and some argue it conflicts with standard inflationary predictions. But it has not been mathematically ruled out. Inflationary cosmology allows physical possibilities in regions beyond our sight that standard frameworks within the horizon simply do not contemplate. What makes this genuinely strange is the scale being proposed. The structures cosmologists have already mapped defy easy comprehension on their own. The Shapley concentration spans hundreds of millions of light-years. The Hercules Corona Borealis Great Wall spans several billion. These are observable structures, reachable by telescopes that exist right now. The claim behind dark flow is that structures larger still, possibly far larger, lie outside the boundary we can never cross. The Milky Way would be falling towards something it can never directly observe. Governed by physics, it can never fully test. Embedded in a universe genuinely larger than any measurement will ever reach. Even if dark flow turns out to be a statistical artifact, even if Koszaliński's signal eventually dissolves under better analysis, the question does not dissolve with it. Is there structure beyond the observable universe? Inflation says almost certainly yes. Is any of that structure large enough and near enough to our horizon to influence what happens inside? That is genuinely open. The answer will not come from a single observation. It may not come at all, but the question is precise. It has a mathematical shape, and the next generation of surveys will at least tell us whether the signals inside our observable universe are consistent with influence from outside it. We live in a universe we can only partially see. That sentence is not poetic. It is the honest description of our situation. In 2023, the Cosmic Flows 4 catalog was released. It was the most complete peculiar velocity survey ever compiled. Over 56,000 galaxy distances, coverage extending to roughly 600 million light-years, when the team ran the bulk flow analysis, measuring the coherent streaming motion of all galaxies within a large sphere of the local universe. They got a number between 380 and 430 kilometers per second, in a direction consistent with earlier surveys, consistent with motion toward the Shapley region, persistent across multiple analysis methods, statistically robust within the catalogue's own uncertainties. Under lambda CDM, the expected bulk flow at those scales is much lower. The standard model predicts smoother, smaller motions. The probability of finding a bulk flow as large as cosmic flows, reported by chance within a universe governed by lambda CDM, is approximately 1 in 650,000 at certain angular scales. Pause on that number. 1 in 650,000. This is not the kind of number scientists set aside. A 1 in 1,000 result might be noise. A 1 in a million result is a signal that demands explanation. 1 in 650,000 sits at the edge of that threshold. It is the kind of probability that makes physicists recheck their analysis 3 times before publishing. The cosmic flows, 4 team checked. They published. Then, in 2026, a prior free reanalysis of the cosmic flows, 4 data appeared in the literature. It addressed a potential systematic error called survey anisotropy. The survey is not perfectly uniform across the sky. It covers some regions more densely than others. A non-uniform survey can introduce apparent bulk flow signals that are actually artifacts of the sampling geometry. The prior free reanalysis applied corrections for this effect. After correction, the bulk flow signal dropped significantly, down to roughly 75 to 80 kilometers per second in some interpretations of the corrected data. That sounds like a resolution. It is not. Even 75 to 80 kilometers per second leaves measurable tension with lambda CDM predictions, smaller tension that can be addressed with some effort, but tension that does not go to zero. The anomaly shrank. It did not disappear. Here is the pattern worth watching. Every time a bulk flow anomaly is analyzed, corrected, reanalyzed, and corrected again, a residue remains. It never fully reaches zero. It never fully matches what the standard model expects. Each new analysis finds a slightly different answer, but none of those answers lands where lambda CDM would predict. This is the behavior of a real signal partially obscured by measurement challenges. That is one interpretation. The other is that the residue is the accumulated effect of small, systematic errors that no correction has yet fully identified. Both interpretations are held by serious researchers, and both lead to the same honest conclusion. Cosmic flows, found something the standard model of cosmology does not comfortably explain. As of today, no analysis has fully explained it away. The number sits there, patient, waiting for a better theory, a better correction, or a deeper catalogue to finally put it to rest. Every measurement of the Milky Way's velocity is also a measurement of the universe. This deserves more than a passing acknowledgement. When astronomers track our galaxy's peculiar motion, the component of movement that cannot be explained by local expansion, the fraction that must come from gravitational attraction, they are not just mapping a destination. They are reading the gravitational field of the universe across hundreds of millions of light years. They are reconstructing the distribution of mass from the motion it produces. Gravity does not announce itself directly. You cannot point a telescope at a gravitational field and photograph it. What you can do is watch how matter moves in response to it. The Milky Way's velocity is the record of every significant mass concentration within the reach of our galaxy's gravitational history. Speed and direction encoded across cosmic time. The CMB dipole is the clearest expression of this. The cosmic microwave background arrives at Earth with a slight asymmetry. One side of the sky is fractionally warmer, the other fractionally cooler. This asymmetry is caused by our motion relative to the CMB rest frame. We are moving at roughly 600 kilometers per second toward the constellation Centaurus. That number is confirmed. That direction is confirmed. Multiple independent measurements converge on it. Everything else in this story, the Great Attractor, Shapley, the bulk flow anomalies, the convergence depth problem, is an attempt to explain why the CMB dipole has the value it has. What mass, at what distance, produces the gravitational pull that sets us moving at exactly that speed in exactly that direction. If that motion is anomalous, the structure producing it is anomalous. More clumped than lambda CDM allows at the largest scales. Cosmologists now use peculiar velocity surveys to do more than identify attractors. They use them as precision tests of the standard model. A velocity field that matches lambda CDM predictions confirms the model's accuracy at large scales. A velocity field that persistently deviates from those predictions is evidence that something is missing. Cosmic flows. 4 is a test of exactly that kind. Every peculiar velocity catalogue before it was as well. The Dark Energy Spectroscopic Instrument Survey, now underway, will be the largest test yet. The Legacy Survey of Space and Time at the Rubin Observatory will extend that further. Euclid's galaxy shape maps will add a different kind of constraint. The next several years will produce, by the reckoning of several working cosmologists, the most informative period in the history of this question. Not because a final revelation is guaranteed, because the data density is about to increase by orders of magnitude. The surveys now underway will map the velocity field to depths and densities that no previous generation could approach. When those maps are complete, the anomalies will either resolve, the bulk flows will shrink toward lambda CDM expectations, the model will be confirmed at new precision, or they will deepen. The universe will look genuinely stranger than the framework allows. One answer confirms, the other breaks something open. Both answers matter, and we will know which one it is sooner than most people realize. The instruments are already running. The Dark Energy Spectroscopic Instrument sits on a telescope at Kitt Peak Observatory in Arizona. It began its main survey in 2021. When complete, it will have measured the redshifts of roughly 40 million galaxies and quasars, spanning 11 billion years of cosmic history. From those redshifts, peculiar velocities can be extracted. Bulk flows can be mapped to depths and densities that no previous survey approached. DESI does not just extend what cosmic flows 4 began. It multiplies it by an order of magnitude. Where earlier catalogues measured thousands of galaxy distances, DESI measures millions. Where earlier surveys covered patches of sky, DESI covers a substantial fraction of the full sky in extraordinary detail. The velocity field it produces will be the most detailed 3-dimensional map of gravitational motion ever assembled. In Chile, the Vera C. Rubin Observatory is entering its operational phase. Over 10 years, its legacy survey of space and time will photograph the entire southern sky repeatedly, accumulating a dataset so large that its volumes are measured in petabytes. Among its many scientific goals, it will identify hundreds of thousands of Type Ia supernovae, the same standard candles that revealed cosmic acceleration in 1998. Each one is a distance measurement. Each distance measurement is an input to the peculiar velocity field. Hundreds of thousands of new data points, where previously there were hundreds. In space, the Euclid satellite is already operational. Launched by the European Space Agency in 2023, it is mapping the shapes and positions of billions of galaxies across the past 10 billion years of cosmic history. Its weak gravitational lensing maps will reveal the large-scale structure of matter with precision no ground-based survey can match. And it will carry Kashlinsky's near-bird instrument, testing dark flow through near-infrared measurements entirely independent of any previous method. Meanwhile, the Meerkat radio telescope in South Africa is actively working through the zone of avoidance. Dense dust in our own galactic plane blocks optical telescopes from seeing the structures directly behind it, a region that includes mass concentrations directly relevant to our peculiar velocity. Radio waves cut through that dust. Meerkat is cataloguing galaxies in the hidden zone, filling in blank patches that have persisted on maps for decades. Within 10 years, data from these 4 instruments will intersect. The bulk flow anomaly detected by cosmic flows. 4 will be tested against a catalogue 20 times larger. The CMB dipole tension will face the most complete galaxy distribution map in history. The zone of avoidance will be substantially illuminated. The convergence depth problem will either close, the mass accounting will add up, and the model will hold, or it will stay open with data this complete. And if it stays open at this level of precision, that will not be a measurement problem anymore. That will be a physics problem, a genuine gap in our understanding of what the universe is made of and how it behaves at the largest scales. The investigation is not winding down. The resolution is sharper than it has ever been. The surveys are deeper than anything before them, and the anomalies are still there, waiting to be explained or confirmed. We know more about where the Milky Way is going than any human generation before us. We know the speed, roughly 600 kilometers per second relative to the cosmic microwave background, confirmed, measured by multiple independent methods across decades of observation. That number is not going to change significantly. We know the direction, toward the constellation Centaurus, toward a concentration of mass roughly 150 million light-years away, and beyond it, toward the Shapley concentration at 650 million. The direction has held steady across progressively better observations spanning 30 years. We know the structure we belong to, 500 million light-years of gravitational watershed containing the equivalent of 100 million billion stars, with our galaxy sliding inward along invisible lines of gravitational force toward a center it will never reach. We know the void at our back, the dipole repeller, an enormous, underdense region pushing us forward as surely as any attractor pulls us. We are drawn towards something. We are also expelled from something. Both forces right the path. We know we will never arrive. Dark energy makes it mathematically certain. The fall is permanent. The destination recedes. The freefall continues without end. And we know the model has cracks. Lambda CDM has carried cosmology for 25 years, and it has earned that trust many times over. But the bulk flows are persistently too large. The dipoles do not fully align. The large-scale structures push against the smoothness the model requires. Every correction leaves a residue. Something remains unaccounted for, and the residue does not shrink to zero the way systematic errors are supposed to. There are structures behind the galactic plane that no optical telescope has fully mapped. Radio surveys are finding them now, slowly, frequency by frequency. Each new mass discovered behind that dust shifts the gravitational accounting. The picture has blank spaces that are only now being filled in. There are depths beyond current surveys where the convergence problem might finally close, or where it might push the unresolved source of our motion even closer to the horizon, closer to the edge of what any instrument can ever reach. The next generation of catalogues will get there within this decade. There is Kashlinsky's instrument aboard Euclid, waiting to test a hypothesis that has been contested for 18 years against a completely independent dataset. That test will produce a number. The number will either close the argument or reopen it on entirely new terms. There is the next anomaly, the one that has not been named yet, in a dataset that has not been released yet, from a team that is right now checking and rechecking a result that does not quite match what the model predicts. The history of this field is a sequence of those moments. The next survey is already collecting light.